Welcome to my talk, Principium, diving into the quantum hardware ecosystem. And today we are going to look into the quantum hardware picture that is there and what quantum hardware means, what are the different global scenarios that we are looking into, and what the current and the future of Indian quantum ecosystem looks like, and what are the different use cases that we'll be going through. So moving forward with the topic and the talk today. So before we dive deep, I'll just give a brief intro about me. So my name is Archit Srivastava, and I have been fortunate enough to found AKM along with my colleague, which is a quantum hardware community focused on improving and spreading knowledge about what the quantum hardware is. And I have also in my college days founded Circuit Quantum Research and in my college, which was RV College of Engineering. And in Quantum Computing India, I along with few of my colleagues, we were fortunate enough to found the quantum hardware learning circles that were there. Over there, I also worked on various use cases and various topics, and it is a very good platform where we can learn a lot of things. In my final year of college, I was the quantum computing intern at Boswan QSI Private Limited. Currently, the company is one of the leading firms in quantum simulations in CFD field. I am also a quantum evangelist at Inogress, where I'm working on the GKQCTP project and how it can help India in the coming years. And currently, I'm working as a senior technical consultant at O9 Solutions, Bangalore, Karnataka. And personally, I'm more interested in solving use cases of quantum computing where we can look into how to integrate quantum computing in the areas of astronomy, astrophysics. If we look at the motivation of the topic, so there is a lack of knowledge about quantum hardware ecosystem and the need for growth in the domain. And we need to increase and spread awareness about various topics related to quantum computing hardware. And there is an immediate need for people to indulge in the development of quantum hardware to realize effective quantum computing solutions in future, because without effective quantum hardware solutions, we cannot essentially look at having optimized quantum software solutions also. So looking at today's contents, what we have is first we'll look into the introduction of quantum hardware. Then we'll have a global picture, then how the Indian landscape looks, and we'll also look at the different use cases that are there. So a brief, not so brief introduction about what the quantum hardware is. So when we talk about quantum hardware, people think that this is a quantum computer and this is the only hardware. But this actually is not the only picture that we have. So this is a relatively bigger picture, and if we see here, this is what the scale looks like. So we have the qubit signal amplifier here, the input microwave lines, the superconducting coil lines, also the cryogenic insulators, quantum amplifiers. This is the mixing chamber that we have here, and various other components like cryogenic shields and everything. And we have various temperature gradation happening also. So as we move down the dilution refrigerator, the temperature decreases, and at the bottom of the contraption, we have the qubit sitting where the temperature is nearly 10 millikelvin. So I don't think it will be fair enough if I call this as the complete picture that we have right now. If we look at the bigger picture more, so this is what a quantum computer mostly looks like. So this was the thing that we think is a quantum computer, but actually this whole picture is what the quantum computer comprises of. So we have the qubit at the lowest end, we have amplifiers, we have microwave electronics, we have the software solutions also, and various things that we have here. So there are different readouts, there is computation going on, and a lot of things happen when we send signal and we receive signal. and how the circuits are connected. So it is not just the dilution refrigerator or the picture that we generally see of a quantum computer, which can be called as a quantum computer. But according to me, this is what the whole picture of a quantum computer looks like. What is under the hood of a quantum computer? We have first we have the user interfaces, as we saw in the previous diagram. There are quantum algorithms and applications, logic level compilation, circuit optimizations happening, quantum error corrections, hardware optimizations, and various stuffs happening, along with quantum firmware, which is called as the hardware error mitigation. We have various things on that level, and the physical qubit hardware that we have finally. A generic quantum classical interface, how it looks like is the quantum classical interface involves several key elements required for quantum computing, control, and readout subsystems. So these systems are distributed between the room temperatures at 100 millikelvin, and as we saw that the temperature decreases as we go down. And we also have a readout transceiver equipped with an integrated field programmable array, or FPGA. And there are various D2Cs, ADCs, which allows a simultaneous readout of multiple qubits. We also have a cryogenic CMOS brown chip that addresses the input-output bottleneck that is there. And we also have various qubit test platforms that are there, and qubit planes, readout multiplexings. We have various applications, quantum algorithms, error corrections happening here, along with qubit control and the classical computer. And we have controlled readouts along with the routing and IO management, and readout multiplexings also happening. And at the bottom we have the quantum chip that is there. So if we look at the circuit diagram also, so it looks something like this, that we have readout resonators, readout transceivers, readout control, we have a DAC, and as we move down, the temperature starts dropping. And this is a picture what is happening on a very granular level that is there. So if we move forward with the talk, what we have here is the how the quantum computer looks. So if we look specifically at the dilution refrigerator, so we have various parts like quantum amplifiers, cryogenic shields, quantum signal amplifiers, input microwave lines. And in a general or a very bird's eye view picture, what we have here is the things that are happening in various quantum computing fields, are the quantum computing theory that happens on the quantum complexity theory and the quantum algorithms. In the quantum programming, we have this layer, and in the quantum computing architecture, we have the system organizations and quantum micro architectures. We have the QVC and FT implementations, classical control, interconnections, topologies, and floor plannings, technology building blocks, which are the qubit interconnect technologies, qubit storage, and gate technologies. There are various qubit architectures that we can look, and this personally are my three favorite illustrations, beautifully drawn by my colleague Abir Vaishnav. So superconducting qubit, trapped ions, and photonic, these are very common architectures, and there are various architectures that we may look into. So if we look into the superconducting qubit that we have here, this is what a superconducting qubit looks like. And we have resonators, we have so in this picture we currently have 5 qubits, and qubit 1, qubit 2. So these are various qubits, and there are resonators in between and there are lines for input and output that we can have. And this is a picture of the Condor chip that IBM announced, and it has 1,121 qubits that are there. And on a very bird's eye view scale, this is what the qubit architecture looks like. If we talk about the ion trap qubit architecture, we use laser beams to control ions. To address the two arbitrary ions in the string of trapped ions, it can be done with beams, the red ones that we have here. And this method can entangle two arbitrary qubits on the string of ions that are there. So the basic principle that goes are the entanglement and superposition of the qubit. So this is how we realize an ion trap qubit. So if we look into another simplified model of a compact ion trap quantum computer demonstrator. This actually is a simplified scale model of the quantum computing demonstrator housed into a 19-inch racks which are there. And the modules in the red correspond to the optical systems that we have. And in the green, what we have is for the communications and the readout. The blue is the electronics and amplifiers, yellow is the fiber routing and switching, and the purple is for miscellaneous of the core module. So what we see here is basically a concept of a compact ion trap computer demonstrator. And this is from a paper named as the compact ion trap quantum computing demonstrator, and it is a very good paper to get an idea about the concept. Moving forward, we also have the photonic qubit that we have. So in photonic quantum computing architecture, photons are basically used as the basic building blocks of a quantum computer, and photons are basically entangled and sent into superposition, and the readout results are then checked and maintained, and various quantum computing solutions are also realized using a photonic qubit. The photonic qubits are also relatively easier to realize than the classical superconducting architecture, which is very popular around. So if we move towards the global picture, how the global picture is looking for the quantum hardware. The current global quantum computing market is approximately valued at $500 million, which was in 2021. It is expected to reach nearly $1.7 billion by 2026. And the major investments are happening from the tech giants like IBM, Google, and Microsoft. And significant government fundings and private sectors investments are happening worldwide, along with rapidly growing interest from sectors like finance, healthcare, and logistics. And these are not the only sectors that are attracting quantum computing investments that can happen. So if we look at the picture of what the quantum computing companies look like, so these are only the 102 companies that are shaping the quantum computing landscape, and it actually is just 102, and it is a very dynamic and constantly developing area where we are having a lot more companies popping up on a daily basis. So we can have a very bird's eye view of what different companies are working on, different technologies. So we have superconducting, photonics, cross industry, and various companies, and we can see very big names also over here, and very new players also that currently are working rigorously in the domain. If we look at how the current global market for the quantum computing is look like. So quantum hardware specifically is marketed is valued at 300 million, and it is projected to grow at 1.3 billion by 2027. And there is an increasing competitions from startups and new entrants, and if we see the quantum computing global market to increase on a daily basis, and there are a lot of investments happening and a lot of innovations happening regularly. And if we look, what will be the long-term benefits, we ask, is the enhanced computational power which we get from these quantum computers are driven to innovation and economic growth of any country that follows it. It accelerates advancements in AI, cryptography, and material science. It attracts high tech investments, talents, and boosting GDP, thus increasing the employability in any country, and strengthens national security through advanced encryption and defense capabilities. Because quantum computing, not in a very generic sense, is very vast, and quantum cryptography, as mentioned above, is one of the key areas where a lot of development is happening globally, and it will increase the security landscape drastically that we can have. And it promotes leadership in the global tech landscape also, and along with various international collaboration. So it is not only if a country is developing the a quantum computer or the quantum hardware the ecosystem, but it happens based on how things are looking, and how intercontinental or inter-country relationships work, and it increases the level of the technology that we have, and any country that is investing in also increases the chances of a better inflow of technologies amongst them. And if now we look at how the future looks like, so the expected market size of quantum computing is 2.5 billion by 2030. uh, there is a continued exponential growth in the R&D investments, increased partnership between academia, industry, and government, and rapid improvements in qubit scalability and stability, broadening application areas like healthcare, finance, and climate modeling. And the quantum computing, like very various fields that we have in major mega science projects along the globe, is a intersection between academia, industry, and government. And quantum computing for any nation cannot be realized without the interaction and involvement of all these three together. So it is a very holistic space where all the three come together and develop the whole country together. And looking more at India, so how the Indian landscape looks currently is, the India is coming out as a key player in the strategic investments for quantum computing, and national quantum missions and technologies and initiative that government is promoting is actually helping the ecosystem to grow a lot. And a lot of startups are coming on a very regular basis, and research institutions and academia collaborations is increasing along with industry and the startup ecosystem that is existing in India. And there is a focus more on quantum cryptography, simulations, and AI applications of India, because it serves as the need for the hour for the development of various other technologies in India at various scales, and for other future technologies for the quantum computing field. Government is supporting various R&D projects, R&D initiatives, assigning budgets and fundings, and development of skills in quantum technologies. We also have these are very like one of the places where and institutions, communities, college groups which are promoting quantum computing at various levels, and both professionally, in academia, in industry. And I'm really sorry if I miss out on a lot of new upcoming initiatives or companies, and these are very few of them which I could have a grasp of. And I'm really fortunate enough to have been part of a few of them from this. So Quantum Computing India, Boson QSci, ICHIM, Circuit, Inogress, Kino Labs, QPI AI, IISc, IIT Madras, TIFR. And these are various quantum computing communities, companies, college societies, uh, initiatives, and colleges, universities, which are day in and day out working together to bring up the quantum computing and hardware ecosystem in India. If we look at the National Quantum Mission, which the government of India has initiated, so it is intended to invest approximately 8,000 crores of Indian rupees over 5 years, which is focused on fostering research and development and deployment of quantum technologies, focus on quantum computing, communications, and sensing applications, which will help in development of skilled manpower and establish quantum labs and test beds. Where which will help position India as a global hub for quantum technologies and innovation. And if you look for future of India, so because of the heavy investment of government of India in by the help of National Quantum Mission, we are going to have an increased ecosystem of quantum computing in future, and we currently also see a lot of quantum computing initiatives and companies coming up on a daily basis, and they are fostering creating jobs in various areas. Strategic partnerships with academic institutions and international quantum research centers are also in place and are happening on a daily basis, and they are increasing the academia industry interactions that happen. And there are a lot of emerging startups which are focusing on quantum hardware development, and it is expected to that the quantum computing market share of India will increase in the future in the Asia Pacific region and also globally. And India is anticipated to be one of the biggest contributors in the quantum technology globally by 2030. And focus on sectors like cybersecurity, health, finance is underway, and various projects are happening in India which are focusing on this, like QNO Labs and various other communities and companies working on it. And India aims to establish it as a significant player in the quantum computing landscape that is there. So if we look at the various use cases that quantum computing can address, so what we have with us is a varied variety and an infinite amount of possibilities that can happen. So we have protein folding, quantum chemistry, design optimizations, supply chain inventory optimization, disease risk predictions, finance modeling, and portfolio optimization, and various other. So these all areas where quantum computing will be implemented based on the quantum hardware that we'll be having, will help in addressing various scenarios and use cases in our daily lives in the longer term, say 50 years or 100 years, and achieve innumerable possibilities that we cannot even think of as of now. And giving a brief about a very interesting topic. So this was my talk that I gave at Conf42 last year, and its name was In Ignitus, and I tried to touch very slightly on how quantum computing can be used in the area of astrophysics. And this I presented as my personal interest about how it can be related to a very different field, and how it can help in the development of that. So please check this talk out, and if interested, just reach out to me on LinkedIn. And I hope that this talk gave you some information about how the quantum hardware ecosystem looks like, and what quantum hardware actually is. And I wish you a great day. Thank you.